Hello, everyone. We are an undergraduate research group from the Department of Electrical Engineering of the University of Moratuwa, Sri Lanka. Our team members are T.I. Hetiarachi, KLM Pereira, and JAAS Kumara. Our research is conducted under the supervision of Dr. R.M.M. Ruwanthika and Mr. Arunya P. Senadira. The topic of our research is development of a sensorless-based bimanual telerehabilitation robot for hemiparetic post-stroke patients. This presentation will cover introduction, literature review, method, control unit, physical system, testing, result and discussion, conclusion, and future work. Let's begin with an overview of the problem statement. After a stroke, the nervous system becomes dysregulated, leading to paralysis in many patients. A significant portion of stroke survivors experience hemiparesis, which results in the loss of interlimb coordination, particularly in the arms. The paretic arm requires intensive rehabilitation to regain functionality. Before discussing the rehabilitation process, it is essential to understand the biological background of recovery. A stroke causes damage to neural pathways, but the brain has a remarkable ability known as neuroplasticity, which allows it to reorganize and form new connections to restore lost functions. Physical exercise plays a crucial role in this process. In upper limb rehabilitation, two fundamental movements are essential. There are flexion and extension, internal and external rotation. Rehabilitation methods can be broadly classified into two categories: conventional therapy and robotic-assisted therapy. Due to the limitations of traditional rehabilitation methods, such as the need for continuous therapist supervision, robotic approaches have gained significant attention. Bimanual coordination during rehabilitation exercises is particularly effective in promoting faster recovery. Here is a summary of key findings from the literature. Robotic-assisted therapy has been shown to be one of the most effective methods for restoring neural circuits in post-stroke patients. Research suggests that a large proportion of stroke survivors experience one-sided disability, and bimanual coordination can significantly enhance recovery. Various wearable sensors, such as EMG and force sensors, are commonly used to monitor patient movement. A study introduced an upper limb telerehabilitation system using force sensorless dynamic gravity compensation. This system employs master and follower robots to provide a transparent haptic experience between the therapist and the patient. Another study developed a mathematical model to calculate the mass moment of inertia of the human arm, which we can use to create a mathematical model of an arm. Research has also demonstrated that torque generation in the arm varies with angular position, making it essential to follow a torque profile for effective rehabilitation. Considering these insights, we propose a bimanual rehabilitation robot with the following key features: bimanual rehabilitation exercises to promote neuroplasticity, a sensorless torque estimation method using disturbance torque observer DOB and reaction torque observer RTOB, no reliance on wearable sensors, making the system more comfortable and user-friendly, real-time monitoring and evaluation, allowing both patients and therapists to track progress, independent exercise capability, enabling patients to train alone while therapists can assist multiple patients simultaneously. The main objectives of our project are to implement 2 rehabilitation exercises using a 1D-off robotics system, to enable shoulder-relaxed upright positioning during exercises, to provide real-time control and monitoring for both patients and therapists. With this system, we aim to enhance stroke rehabilitation by making it more effective, accessible, and scalable. Now, let's move on to the method and control system we used. This is the simplified system block diagram. Here, the master motor connects to the healthy arm and the follower connects to the paretic arm. If we look at the master side, the motor gives resistant torque to the arm and the arm moves against it. Using the master speed and current, the DOB estimates the disturbance torque, or the total load on the motor, and the RTOB estimates the external torque produced by the arm. External torque is the feedback for the proportional torque controller. It generates a current command to control the external torque to match the torque profile. The disturbance current derived from the DOB is added to that so the motor always overcomes the applied load. This makes the control more robust. The follower side is almost the same, but the problem is we cannot control the paretic arm torque to the profile because it cannot generate that much torque. Our goal is to train the paretic arm. To do that, we must move both arms simultaneously. However, under the same set torque from the profile, the paretic arm will lag behind the healthy arm. Therefore, it needs assistance. We provide that using a virtual spring. Here, a torque is calculated proportional to the lag and is reduced by the set torque from the profile to simulate assistance. Before going into the detailed block diagram, which explains the complete mathematical model of the system, these are the terms used there. Here we have the master side. There are DOB and RTOB blocks, the motor model, and the proportional torque controller. Gravity compensation is also added to account for the weight of the arm and the robotic arm. In the follower side, all other things are the same except for the assistance torque, which is proportional to the position difference. It is reduced from the torque profile. To further understand the torques in the system, this diagram shows the torques in the flexion motion. The arm torque is upwards and the resistance is downwards for both arms. The assistance to the paretic arm is upwards. If we derive the equation from the mathematical model of the system, first we have the DC motor model, where torque is given by inertia times angular acceleration. Then the DOB, which simplifies into the disturbance torque. Next, the RTOB, which simplifies into the external torque, excluding frictions. Using these torques, the proportional controller derives the command current to the master motor. The same process is done for the follower motor, including the assistance.